Hi guys, Manuel again with the next installment of the Particles course. We are counting to 5 today. This is episode 5 and today we want to have a look at a very important pop, the replicate pop. Pop replicate. That is used to split particles into more particles. It is very useful for creating effects like fireworks, but you can do more. You can use particles to create procedural geometry too. And today I want to use the pop replicate to create growing plants, a field of growing plants. This is quite neat because you can just scatter particles anywhere and the plant will grow. So let's directly dive in and get started. Let's drop a geonode, geometry, and let's call it particles. Now, let me switch on my parameters and let's dive inside. Let's create a surface for the particles to grow on. So for now, let's just use a grid. And let's increase the resolution a little if we later on want to put attributes on this grid, like so. And now append a scatter, as always. And for now, let's only scatter 5 points. Because we want to, let me make the points a little bigger such that you can see them better. We want to build our effects using few particles, and as soon as everything works, we can increase the count. Now, we have these particles on the surface, and the plants should grow upwards. So, let's drop a wrangle, a point wrangle, to initialize the velocity on these points that will be turned into particles later. And let's state v at v, which is the velocity, should be the vector, brackets, and semicolon, 0, 1, 0, upwards velocity. And create a popnet. Wire this in. Let's make the popnet visible, and let's dive inside. And let's quickly set the pop source, as always, to use all points. And if we now press play, the particles are flying upwards, or a lot of particles are generated, and because of the initial velocity, everything is flying upwards. Now, we only want to use the points that we initially scattered, so only these 5 points. So we have to restrict the birth. So go to the birth tab. Let's put a little expression here in the impulse activation. $f, that is a frame, should be smaller than 2. Then this expression evaluates to 1, and the birthing is activated. So now we have 1 particle per input point. These blue dots here are just the guide geometry. Let's turn it off. So now we have 5 particles moving upwards. We don't want these particles to fly upwards forever. They just should fly up for a certain amount of time, and then they should come to a stop. So one way to achieve this would be to just dial down the life expectancy. So if I go to 2 here, say, these particles will die after 2 seconds. But as I plan to attach leaves to these particles later on, I want them to stick around. I don't want them to vanish. So instead of dialing down the life expectancy, put it back to 100, I want to use a different method to make them stop. As soon as they are born, I want to initialize a new attribute on them called stop with a time. And as soon as the age of the particle exceeds this time value, we just set the velocity and everything to 0 and the particles will stop. But how can we initialize attributes on these particles? Well, we can use a wrangle, a pop wrangle, and I can attach it here. But this pop wrangle will be executed in every frame. But there is a neat trick. We can specify a just born group. Let's do that. And let's call it A_born. And for this name to make sense, let's call the source first input A. That's our first particle stream. This pop wrangle should only be executed for this just born group. The particles that are created are inside of this group for exactly 1 frame. So if I take group here and call it A_born, is this a group name I used? A_born? The code here will only be executed 1 frame after creation of the particles. So we can use it to initialize values. So let's go in here and let's create a @stop attribute. @stop. And let's set it to 2 for now. Great. So now we have this @stop value. but nothing changes because we have to make use of this value. So let's create a second wrangle, a second pop wrangle, after the first one. And for clarity, name the first one initialize. Say initialize A. And the second one, let's call it stop. In the code field for this second wrangle, we can write something like, if the age of the particle is bigger or equal to this created stop value, stop, then let's just delete v at v, or set it to 0, like so, 0. So let's see what happens now. Now the particles are traveling upwards, but as soon as the age of the particle is bigger than the stop value, the particles come to a halt. That's exactly what we want. They are traveling upwards and then they're stopping. To make it more interesting, let's vary the stop values. Instead of giving everybody a 2, let's write an expression fit and then rand at ID. So this generates a random number from the ID, and as we ticked add ID attributes here on the attribute field of the pop source, each particle will get a unique ID. Now we can use that. So random ID, and then we want to fit it. The random function returns the value between 0 and 1, so 0 to 1 is the input range, and the output range should be between 2 and, say, 5, like so. 2, 5. Now they get different values. Let's see if this has the desired effect, and it has. Now what bothers me is that they're stopping very harshly. So they are just traveling and then boom, they are stopping. It would be nice to have a little easing effect, and we can easily do that because this is a simulation by changing this code. Instead of just setting the velocity to 0 once the stop value is reached, let's instead just vary the velocity. So let's write v times equals 0.9. That is a shortcut syntax for writing v should be v times 0.9. This times equals means just multiply 0.9 by the velocity and set it to the velocity. So that means now the velocity is just decreasing. Let's see what this gives. Not much because I have a typo. 1 equal sign too much. So let's see what this gives. And you see now they are easing out. They are still coming to a stop, but they are easing out. Nice. They are still just traveling upwards in a straight line. It would be nice to give them some random movement, and we can do this by using a pop force. The pop force can be used to dial in a force. Let's put this pop force here between the initialize and the stop. But we don't want to set a force directly. Instead, we want to use the noise feature of the pop force. So let's set the amplitude of the noise to 1 and the swirl size to, say, 10, like so. And let's see what happens. Now they are dancing around. They are not moving upwards in a straight line anymore. Let's tick the stopwatch to have real-time feedback. And now you see they are behaving quite naturally. Okay. Now I want to make them into primitives. I want to create passes from these particles. And these passes should be the stems of our plants. The first thought that comes to everybody's mind is the trail sop. But be careful, because the trail sop just automatically creates trails. And that means as the particles never die, the trail sop will add points and points and points and points all over again. And I just want to add points as long as the particles are moving. As soon as the particles stop, I don't want to add points anymore. So instead of creating trails with a trail sop, I will do the trails manually. And for that to work, I want to create new particles from these 5 initial particles. And that is where the pop replicate comes into play. So let's see what we can do here. Let's create a pop replicate. The pop replicate has 2 inputs. And these two inputs have different functions. The first one is using the particle stream that comes in to replicate points, and the second one is using the particle stream as a reference. I explain later what this exactly means. For now, we just want to put the pop replicate here between the stop and the wire pops into here. And you see, as soon as I do that, I get a lot of points, because the pop replicate does its job. If we quickly glance over the attributes of the pop replicate, we have a birth tab here that resembles exactly the settings of the pop source. And then we have this shape tab, and it is set to sphere. That means that the particles that are newly created are scattered in a sphere around the initial particles. We don't want that. We want to replicate the particles exactly where they used to be, so set this to point instead. Now everything goes away, but the particles are still there. It's just that they all happen to be in the exact spot of the input particles. And then you have noise, and you can deal with attributes. Again, you can create ID attributes, and you have stream and binding tabs. So great. Go to the birth tab again, and at the moment we have constant activation set to 500. We don't want that. Set this to 0, because we want to create one particle per input particle per frame. So instead, set the impulse count to 1. Let's rewind and see what happens. Okay, these particles are replicated, but they really move in a very odd way. What is happening here? Well, to understand this, we have to go to the Attributes tab. And here, this initial velocity dropdown is set to use inherited velocity. That means that the newly created particles inherit their velocity from their parents. We don't want that. We want to have the velocity set to 0 when they are born. So instead, set this to set initial velocity. But be careful, the variance value of this velocity is set to 1 by default, and that means although I set the velocity to 0, particles will get different velocities. So set the variance to 0 too. So let's see what happens now. And now it looks as if a neat trail of particles is created. But if you have a close look, they are still wiggling around. So why is that? Well, when these particles are replicated, they inherit all the attributes from their parents. And as we set this pop force here, the parents have a force value applied. And as these are just particles, this force value will be integrated to velocity, and that means although we set the initial velocity to be 0, the force creates new velocity. So here with the inherit attributes field, at the moment all the attributes from the parents are inherited. But we want to exclude the force. So put a little hat here, that is the syntax for excluding certain attributes, and then force like this. And let's see what this gives. Now we are just creating trails that are following the movement of the initial particles. That is exactly what we need. But if you turn on point numbers and have a close look, you will see that although the particle is stopping, new particles are still being created. So we didn't gain anything from doing this pop replicate over the trail stop. But we can use a feature of the pop replicate, and that feature is emit from attribute. So we can set an attribute on the parents that determines if new particles are created or not. So tick this on, then this attribute field is activated, and let's put an attribute here, trail. This attribute is not existing at the moment, but we will create it immediately. On the parents, go to the initialize, and let's create this trail attribute. At trail is 1 means please replicate particles. And it replicates particles. Now go to the stop, because now we can prevent the particles from being created once the stop condition takes over. So here in this if clause, we can say at trail is 0. So as soon as this condition is true, trail will be set to 0, and that hopefully means that no more particles are created. And you see this works. But the problem is that our particles are not stopping immediately because of this easing effect. So we have to get a little bit more sophisticated to create new particles as long as the particles are moving. And this can easily be achieved by extending on this if clause with an else if, and here we just say length, so the length of the velocity vector, v at v, should be smaller than 0.01. And if this is the case, please execute the code that comes between the curly braces, and the code here should be add trail is 0. So instead of setting the trail attribute immediately to 0, we just set it to 0 as soon as the length of the velocity drops under a certain value. So as soon as the particles are really slow. So let's see what this gives. Seems to work. But they never stop moving. And that is because we missed something. The thing I explained with the force is not only true for the replicated particles, but for the initial particles too. They get a force by the pop force all the time, and although I decrease the velocity, the force will add to the velocity. So instead of just decreasing the velocities, let's set the force to 0 at the same time. So add force should be 0 on the parent particles too. 0, like this. So now it seems to work. No, the particles keep being replicated all the time, and that's probably due to this else if. The else if means this is only executed if this is not true. So let's get rid of this else and just create a second if statement. And this should fix it. And it works. Now this happens, so the else if was not correct. Now we have a bunch of points that are created from the particles, and we can use these points to create trails from them. Let's do this one level up with the add sub. So add an add sub and append it here directly after the popnet. Now we have to tell the add sub what to add. We want to add polygons, and we don't want to add them by pattern. Instead, we want to add them by group. And the method to use is by attribute. We want to specify an attribute that tells the add sub which particles to connect. So we need an attribute that is the same for all of these points. And remember that these particles inherit all the attributes from their parents. So they, in theory, inherit the ID attribute from their parents. So we could use the ID attribute. The problem is that, remember, we ticked add ID attribute on the pop replicate. So the ID attribute is inherited, but then it is overwritten with new IDs for the newly created particles. So we have to create a new attribute that we can use here. Let's do that. So let's dive inside. Let's go to the initialize of the parents, and let's create a new attribute. Let's call it I for integer add connect, and let's set it to the add ID. Now this means I create an attribute with a new name, having the ID, and this is inherited by the newly created particles, although ID attribute is ticked here. So now all the newly created particles inherit the connect attribute of their parents. And hopefully we can use this for the add. So put connect here and make this visible. Rewind and play, and you see it is working. But these lines are closed. So why is that? This is because we are not only connecting the replicated particles, but the initial particles, the parent particles, are still in there. They are included in the geometry, and that confuses the add. So we have to get rid of them. How can we do that? We can use a group, but we don't have to. Let me quickly tell you about particle streams. Streams are just particle groups, but they are created automatically whenever a particle is created. So this pop source here automatically creates a stream. And the name of the stream that is created is defined here. $OS is a H-script expression that just means use the name of the node. And in our case, this is A. And then this name is prefixed with stream. So if we quickly go to the geometry spreadsheet, then to the pop object, and then to geometry, we see all the geometry here. Hide all attributes and just make group attributes visible. If you do that, then you see that we have a group A-born, that is a born group that we created, and then we have group stream A. This group is automatically created by this pop source. And then we have a second group here called group stream pop replicate 1. And that is a stream that is created by the pop replicate. So all the particles that are created by this node are automatically placed in this stream group here. Maybe let's call the pop replicate B instead, makes stuff easier. And now we have two streams, stream A and stream B. And we can use these streams to get rid of the initial particles. So now, one level up, we can lay down a blast and tell the blast stream A, and that means it will remove everything that is in stream A and it will keep everything that is in stream B. Another possibility would be to specify stream B here and then tick delete non-selected, like so. And if we now connect this to the add, you see that these odd closing lines are gone, because now it is clean. Now we have clean values on all of the points, and we can connect the points to create lines. And these lines, if I turn on point numbers, these lines stop growing once the particles stop existing. So now we achieved our goal. We created more intelligent trails. To better see what we are doing, we can use a feature of every object in Houdini, and that is to shade these lines not as just single lines, but to give them a width. We can do this one level up on the object itself, and if you go to MISC, you will see this feature shade open curves in viewport. Let's tick that, and you see now they are shaded, but they are still very thin. But we can change that if we apply a wrangle, point wrangle at the end, and just give them a width value. So if we write add width, that's a standard attribute that is recognized by this shade feature, and say 0.2 for now, you see that now you have a width to these curves. And I think this is easier to see with the width, like that. To clean up, let's call this set width, and then let's apply a color at the very end, because white on blue is not very visible. Let's make them red. Now, clearly visible. Great, so now let's put a leaf at the end of these strands. Let's quickly model a leaf. Lay down a circle. This will be an abstracted leaf, and set the circle to the x-plane. Make it visible, that's our circle. And now we want to cut this circle. I could use a bool for that, but I want to use something esoteric. I want to use a Voronoi split. That's very nice to split something in half. And it works like this. It uses a line as a second input. Line, lay down a line, and if I turn on points, you see this is a line, and what it does is it creates a split at the midpoint between the two endpoints of this 2-point line, like this in this direction. So let's put the line in the correct place. First, let's move the origin to minus 0.5 in x, and then change the direction to 1, 0, 0. That gives this line. And now let's connect it to the second input, and let's see what this gives. And you see, we have a split here in the middle of the circle. Let's put a transform between the line and the Voronoi split. That way we can transform it over. We don't want the cut to be in the exact middle. And now we want to get rid of this part here. And we can do that by telling the Voronoi split which point of the original line should be the part that is discarded. And that is point 1. So in the clip points group of the Voronoi split, put 1. That is point 1. And that is exactly the wrong way. So let's move this to the other direction, like so. This is what we are after. And now we want to mirror this. So let's append a mirror sub. And to mirror it exactly at this split, we can move the origin of the mirror sub. So let's copy this value here, the translate value, and put it here to the origin as a relative reference. And now we get this, our leaf. Very nice. But we have to move it to the origin again to be able to use it as a copy source. So append another transform, like so, and paste a relative reference here, but this moves it even further over because we have to invert this by applying -1, and now it moves it back to the origin. Like so. So we just inverted the transform. But now the origin is in the middle of the leaf, and we want the origin to be at one of the corners of the leaf. So let's move it over. Like so. Now the origin sits at one of the corners of the leaf. So this is our leaf. Let's append a fuse to fuse all the points together. Like so. And let's create a null, just for clarity, and call it out leaf, like so. And now we can use this model leaf to put it on our points. But remember, we blasted the original particles away because we are just keeping whatever is in stream B. But to put the leaves on, we need the particles that are in stream A. So create another blast and put this to stream A. If you make this visible, you see it's just the parent particles. And now we can append a copy sub, copy the points, and just copy the leaf to the points, like that. And now we just merge these leaves with our generated stems. And now we have a trailing leaf, and then it is creating these stems. And the orientation of these leaves is determined by the velocity of the particle, which automatically gives the correct orientation until the particles stop. Remember, to make the particle stop, we set velocity to 0. And as soon as velocity is 0, the orientation does not work anymore. So we have to care about the orientation of these leaves differently. The copy to points can use different methods to determine orientation. It can use the velocity, the normal, or an orient attribute of type quaternion. And it uses a hierarchy. If orient is present, it uses that. If not, it looks for normals, and if they are not present, it looks for velocity. And that is why it is using the velocity to orient our stuff, because we don't have an orient attribute. So rewind and let's create an orient attribute. The problem with our leaves is that they are flipping as soon as the velocity vanishes. So we have to create an orient attribute while velocity is present, but as soon as no velocity is there anymore, we just have to keep the last orientation. And we can do that here in the stop wrangle. So press Alt-E to open the expression editor and try to think a second about what's happening here. So if the age is larger than stop, then the particle will stop. That means as long as this clause here is not executed, we have a velocity. Only if this if takes over, the velocity vanishes. So what we can write is, we can put an else statement here. And this else statement will only get executed as long as this is not true, as long as this is not happening. So we can create the orientation here. And then as soon as this is true, the orientation will no longer be created, but because we are inside of a simulation, the last orientation will just stick and we can use it further. So let's create a new attribute of type vector4 because it is a quaternion. And to indicate that, we use a little p at orient. And this will be a quaternion. But dealing with quaternions is hard. It's easier to deal with 3x3 matrices. Fortunately, we can convert matrices to quaternions by just stating quaternion, like so. And inside we can generate a matrix. And for this we have a very neat function. And this function is called lookAt. LookAt will generate a 3x3 orientation matrix just from 2 points. It wants a vector where the lookAt should start and a point where it should look at. And we start at p, which is the particle position, plus the velocity, v at v, and it should look at the particle's position. And then let's create an up vector to avoid flipping, and the up vector in our case will be the x-axis, so 1, 0, 0, like so. So now, this is a little complicated, but it is easy if you just dissect it. So the lookAt, it's creating a 3x3 matrix from these 2 points. And then this matrix is just converted to a quaternion, and the quaternion is stored in the orient attribute. So let's apply and accept, go 1 level up, and see what happens now. If we press play, the leaves are not flipping anymore, because now they are not oriented using the velocity, but they are oriented with our newly created orient attribute. And this attribute stays even if the velocity vanishes. So now we have a stable behavior for the orientation. Great. So we put a lot of effort into creating these worms. They are not too interesting, but we will make them a lot more interesting by creating little twigs originating from these stems and putting more leaves on them, and then upping the particle count, and eventually it will look great. But that is for the second part of this tutorial. This is already running half an hour, and I think it is enough for you to digest. So stay tuned for part 2, where we put the secondary level of particles on these stems. Thanks a lot for listening. See you next time.